In today's note, we're going to be looking at the line of best fit. This is something that you should have seen in grade 9 and 10, but we're going to be looking at it again and just expanding on it a little bit while still covering or reviewing some of the stuff that we should already know. So the first thing we want to look at is a scatter plot. And a scatter plot is a graph of the independent versus dependent variables, usually with points or dots representing each coordinate. And we use these to look for a relationship between the two variables. So if I look at these two examples here, in my first example, I have a graph looking at agreeableness and behavior problems. And looking at this graph, we should see that there is a relationship that as people become more agreeable, there are fewer behavioral problems. So this is because we can see that as the agreeableness increases on the x-axis, the behavioral problems decrease on the y. So we have this kind of negative slope. In our other graph, we have husband's age versus wife's age. So we can see here that the relationship is that as husband age increases, then the wife's age also increases. And this can be seen because if we look on the x-axis, as it becomes greater or it increases, it does so on the y-axis as well, which is why we get these points going in an upwards direction. So when looking at a scatter plot, there are types of what we call linear correlation. And these are just going to be terms that we can use to describe a relationship or describe a scatter plot. So we have a positive correlation, which means that as x increases, y increases, or using terminology from grade 9 and 10, we have a positive slope. So in the last example, that would be looking at the husband's age and the wife's age. It had a positive slope. Other examples could be as shoe size increases, height increases. A negative correlation means as x increases, y decreases. Or you could think of it as y increases, x decreases. It's basically that they're not the same. As one increases, the other does the opposite. And again, using terminology from grade 9 and 10, this would mean a negative slope. So as TV use increases, reading time decreases, or if you could look at the other example, as agreeableness increases, behavioral problems decrease. Right? Time spent on social media increases, school marks decreases, something like that. So as one increases, the other decreases. So with our scatter plots, we want to make sure that we can identify between independent and dependent variables, because this can help us determine which one is causing the effect on the other one or which one's dependent on the other one. So usually in most cases, the independent variable is always placed on the x-axis. Very rarely is there ever going to be a case where the dependent is placed on the x. And the dependent variable normally is first in the table of values. So when you're looking at a table of values, your first column or your first row is going to be your independent variable. And then the dependent variable is kind of the opposite. So it changes or gets influenced by the dependent variable or independent variable. So it changes or gets influenced by the independent variable, whatever it happens to be. So if I look at the first example, I have income on the y-axis and years of experience on the x-axis. So this means that income depends 1 years of experience. And if I look at the next graph, looking at price and size in carats, so if we're looking at diamonds, the price depends or is influenced by, depends on carat size. So that means that the price would be the dependent variable and the size in carats, or the carat size, would be the independent variable. If we're looking at an example, a car manufacturer collected the following data, looking at speed in kilometers per hour and stopping distance. If we want to determine the independent and dependent variables, well, what we should see, or if we think about the scenario, our first row is going to be our x, and our second one will be our y, or in other words, we have our independent and our dependent variables. So the independent variable is speed, because your speed is not dependent on your stopping distance, but your stopping distance is dependent on your speed. So your stopping distance is the dependent variable, and in other words, you could say that stopping distance depends on speed. So this could be, again, something that you just kind of reason out for yourself based on the scenario. So if we were to graph that image, we would see our speed along the bottom on the x-axis because it is independent, and we would have our stopping distance on the y-axis because it's the dependent, and you would have your graph here. Now you still may get the same shape if you switch the two, but it's not going to read the same way looking at it. So that's why it's important to have the variables in the right spot. Another terminology looking at scatter plots is the correlation coefficient, or R value. So this is a value that you can get your graphing software or your graphing calculator or Desmos or GeoGebra or anything to spit out, and it will give this number to you. And basically what this value is, it's a number from -1 to 1 that gives the strength and direction of variables. So basically it tells you how closely it models a linear relationship, whether it's positive or negative relationship. So if I kind of look at a scale going from negative, whether it's strong negative, moderate, weak negative, to positive, weak, moderate, and strong, I'm having values that go from -1 all the way to +1, and in the middle would be 0. So if you're trying to vary this out, maybe you have -0.67, -0.37, +0.37, and +0.67. So just using a thirds. So these values can kind of tell you whether it's a positive and moderate relationship or a negative and strong relationship. If you have a R value of 0, that means that there is no correlation, or it does not model a linear relationship. And then if you have a 1, that means it's perfect. So the closer to 1, the closer to a linear relationship. And same with the -1. It's considered perfect. It would just be a negative relationship instead of positive. So again, you would be given the R value. You just have to understand what it represents, or use that R value to come up with a conclusion based on your data or your scatter plot. Another R value, or another value, the coefficient of determination is just the r value squared. And this is a number from 0 to 1 that gives the relative strength of the relationship between two variables. So the r value told us how well it modeled a linear relationship. The r squared value tells us what is the strength of the relationship between the two variables. So yes, they could model a linear relationship, but what is the strength between the two variables? And this is given as a percent, or a percent as a decimal. And it is never going to be negative. Because if you square a negative number, you get positive. You square a positive number, you still get positive. So as an example, if you were told that the r squared value is equal to 0.44, this means that 44% of the variation of the dependent variable, or 44% of what the dependent variable is due to the variation of the independent variable. So that means that 44% of the value is dependent on the independent variable, and the rest is due to randomness or other variables that we're not accounting for or we're not keeping track of. So again, it's just another method of determining the relationship between two variables. Regression is another term. It is a mathematical function that describes a relationship between two variables. So if we look at something called linear regression, that means we're looking for a linear model that fits or describes the relationship between two variables. And we've seen a linear regression referred to as a line of best fit. The vertical distance between the line of best fit and each data point is called a residual. So what this means is that if we're looking at the vertical distance of each value away from the line of best fit, that's called the residual. Ideally, the sum of all the residuals should be 0, because we would want every value or every data point to be exactly on the line of best fit, so there'd be no vertical difference. And then the sum of squares of those residuals should be as small as possible. And this criteria is called a least squares fit. So basically, it's just how the line of best fit is created, where you have the sum of the squares of residuals as small as possible. So in example 2, if we want to use Desmos to go through and calculate and graph a scatter plot, we can also use it to determine our regression, our R value, or our R squared value. So for example, if Sarah grew a bean plant in science class, the height of the plant was measured every few days. The data she collected is represented below, where we have day and we have height. So again, we have the first column, or the first row, is our X value. The second one is our Y value. And again, you can do this on a graphing calculator. We're going to stick to Desmos because it's easier to use. You can do this at home without a graphing calculator because you can use the Desmos app or use Desmos online. So you create a scatter plot of the data and change the window again to make sure the settings for the max and min to make sure it fits. And then you can ask yourself, does it appear to be a linear correlation? And when you go through and you enter this data on Desmos, you should see that yes, it does appear to be a linear correlation, because again, we should see it forming very similar to a straight line. Next, what we want to do is find the linear regression, or we want to find a linear function or the line of best fit. So finding the linear regression, just saying the line of best fit. So what you do in Desmos is in a new line, you type in y1, and it should subscript it, approximates a little squiggly line, m, x1, where the one's the subscript, plus b. And when you enter it into a new line, you should see something similar to this in this box here, and it gives you all the values. So your y1 approximate mx1 plus b, and it gives you statistics of your r1, or sorry, your r, which you should have is 0.963. You get an r squared value of 0.9394, or basically 94%. You have your parameters, so this is telling you what your m value is of this linear equation. So your m value should be 0.938, and your b value should be 1.001. So what this tells us is that basically we have a linear equation of y equals 0.938 x plus 1.001, and this linear equation is our line of best fit, which gives us an r value of 0.963, which means it is a strong positive, and an r squared value of rounding to 0.94, which means there's a 94%, or 94% of the variation is due to the independent variable, and 6% is due to randomness. So there is a very strong relationship between the two variables. And that is all given to you in Desmos. If you observe the linear regression in the graph function and your coefficient of correlation, how confident are you that this relationship is linear? Well, because this coefficient of correlation is looking at my r value, which is equal to roughly 0.97, I would say that this is a very strong positive relationship. Because the r value is very close to 1, and it's close to positive 1. So what this is saying is that as days increase, plant height increases. What percentage of variation in height of the bean is due to the variation of the number of days? Well, because my r squared value is equal to 0.94 rounded, or 94%, what this is saying is that 94% of the variation, or 94% of the height, of the plant height is due to the number of days. And this would mean that 6%, or the remaining percent to 100, is due to randomness, or other variables that we haven't taken into account, or we aren't measuring. So what factors may explain the remaining percent? So what other variables could we not be accounting for? So it could be something like the amount of water used. It could be something like the amount of light it gets. It could be the temperature. It could be the soil pH. Any factors other than the number of days would account for that 6%. So, is the growth of the plant linear? Justify your answer. And I would say yes, it is linear. And you could say growth can be approximated by the function, or the linear function, y equals 0.94x plus 1, so just rounding. And you could say due to high r and r squared values. So because those values are high, we could say yes, the growth is linear, and it's linear using this function or this linear regression. The y equals 0.94x plus 1. For g, what will the height of the plant be after 20 days? So this is something that you can use. You can use the equation, you can use the graph. Right? If you're on the graph, you might have to expand out to look at 20 days and just go up to the line of best fit. Or what you can use the equation, because we know that y represents the height or the dependent variable, and x represents the days. You do y equals 0.94 times 20, or 20 days, plus 1. So just using the linear regression or the linear function to actually calculate what the height would be, and we should get that the height is around 19.8 centimeters after 20 days. And then you can do the same thing for 9 days, whether you look at the graph or you use the actual equation. 0.94x plus 1, y equals 0.94 times 9 plus 1. So basically you're just substituting in the value or the number of days for x and solving for y. So 0.94 times 9 plus 1, I get 9.46. So you could say, therefore, there's about the height of the plant after 9 days will be 9.46 centimeters. So some of this may be review, the idea of using a line of best fit, but now we're actually using data software to go through and actually calculate what the function of the linear equation is. And we're also looking at now the correlation and the correlation of variation. So we're looking at the r and the r squared values, just different ways to, again, describe the relationship mathematically.